Record. Okay, so good afternoon, folks. Welcome and thank you for tuning in to another Risk Institute online session. Today, we're fortunate to have with us the wonderful Professor Bilal M. Ayyub from University of Maryland, the A. James Clark School of Engineering. The presentation will be around 45 minutes with around 15 to 20 minutes of Q&A. So please make sure that your microphones are muted. And if you'd like to leave any questions on the chat or unmute yourselves afterwards, then we can have an open discussion. Professor M. Bilal M. Ayyub will be talking to us about hazard resilient infrastructure, including network topology and underground spaces as case studies. So that sounds very exciting. But before we begin, I'd like to make a few announcements of our upcoming schedule. So on the 3rd of May at 4:30 p.m., we have Dr. Divya M. Paswad talking to us about 2D and 3D imaging of planetary surfaces using remote data sets from the NASA Jet Propulsion Laboratory. Following that, on the 10th of May, we have one of our alumni, Dr. Sarah. I'm not going to attempt her last name because I think I might get it wrong, but she's working on Generation Pup, which is the biggest study following dog behavior. I think they have around 10,000 dogs to try and reduce the risk of, say, dog bites and increasing their welfare and reducing, basically improving behavioral measures over the course of their lifetime. Then we also have one of our students, Mr. Vladimir Stepanov, on the 17th of May at 2 p.m. He hasn't given us a title yet for his talk. And Mr. Enrique Morel-Dols, also from our institute, on the 31st of May at 2 p.m. So without further ado, let me introduce our speaker. So Professor Bilal M. Ayyub is an A. James Clark School of Engineering professor and the director of the University of Maryland Center for Technology and Systems Management. He has expertise in the areas of risk, uncertainty, and decision analysis, and risk management, including finance. He has among 650 publications co-authored and more than 20 books, including several textbooks adopted for courses at universities internationally, which is phenomenal. He is the recipient of several research awards and prizes and consulted to national and international organizations on infrastructure, defense systems, on risk, microeconomic, and financial modeling. So I'm sure you'll agree he has a wide range of accomplishments here, and I'm really excited to hear his presentation. So if you'd like to start sharing your screen, and we can begin. Thank you very much.
All right, let me share the screen here. Okay, sharing the screen. Okay, can you see it now? Let me put it in presentation mode.
Okay. Yeah, that's perfect.
Yeah, let me go back. Yeah, let me go back to the beginning here. Okay. All right. Well, good afternoon. Thank you, Francis, for the introduction. I'd like to start by thanking the University of Liverpool for inviting me to give this presentation. I was fortunate to visit the university a few years ago when to attend the conference, and I still, fondly remember that visit. I'd like to thank Dr. Scott Fearson for the invitation and Professor Michael Beer for making the connection. The outline of my presentation is shown in the first slide. I'm going to focus on the hazards in terms of trends and the impacts of a changing climate, and basically the need for resilience of infrastructure, because it feeds and supports community resilience. And I'm going to use case studies focusing on underground spaces in the form of tunnels, and as well as retail and commercial spaces, and the use of networks which connects those spaces through other case studies representing transit systems. And then I'm going to show some results based on an ongoing project that we have on railroads. And at the very end, decision-making is driven by economics. So I'll be devoting a few slides on microeconomics and the socioeconomics of resilience. In terms of the global and national trend, if you look at the top, if you look at the panel, which is the Swiss 3, it shows global catastrophic losses. These are based on insurable assets. And you could see overall, I mean, you could see the rising trend from 1970 to the present. Although you could look at it as it's really, there is an increase in count, but also there is an increase in inventory. But this has been demonstrated not only by counts, but by rates, in number of events per year, or number of, or percent of events, percent of insured assets that were impacted over time. And certainly there is a trend at a global level. If you look at on the national level, when I say national, I mean US national, the panel which is below is from NOAA, and these are US natural disaster events. And again, overall, there is a trend. And what's interesting, according to the World Economic Forum, which they publish a report on an annual basis in the 2020, as well as in other reports in prior years, they show that how risks are interconnected. They classify risks by economic risks, environmental, geopolitical, and so on. And you could see by the size of the diamond and the strength of the link to show the level of interdependence. So you could have a climate action failure, which will lead to extreme weather, which will affect flooding cities and so on. It could lead to unemployment. And there are the message of this figure that when it comes to the consequences of various hazards, it's really a very complex picture because of this interconnectedness and these interdependencies. Another slide, which is in the background, according to the UN, the United Nations Office for Disaster Risk Reduction, over a period of 10 years, from 2005 to 2014, we had $1.4 trillion of direct damages. 1.7 billion people were affected over 10 years, 700,000 fatalities. The 70% of the fatalities are because of seismic hazards. And I could say 70% of the damages, direct damages, are due to flooding. So it's known that flooding is the largest producer of direct damages and losses, while earthquakes, it's the biggest, a source or a cause of fatalities. But there are variabilities, as you could see by the size of the circle or the bar chart. But there is, and the numbers that you have in here, if you divide by 10, it could give you an idea about the magnitude on the average per year, because these numbers are for a decade. The panels on the side, this one shows just the impact of a changing climate. What you have in here, the different colors, they show the cumulative number of storms. This was done by for oil and gas in 2020, and it shows the total number of basically storms from 1979 to 2019 in a cumulative fashion from the beginning of the year to the end of each year. So each color represents a year. And what's interesting, in 2020, when that figure was prepared, it shows the green dots, which is the cumulative count in 2020. And that was done in November of 2020. And it was, far exceeding all the prior years. So, I mean, obviously we have the evidence for an increase in the count of storms. Also, we have an evidence that the intensity is going up, and the return period for a given intensity is going down, which is as illustrated in this figure in here, where the current is what's shown in here. This is the current of storm rainfall versus basically return period. And this is based on projected to the end of the century. And it shows the shift from the blue to the red in terms of the projected, storm intensity or rainfall versus return period curve as a result of a changing climate. Now, the hazards that are of interest to us in order to design and provide for climate or hazard resilient infrastructure, which is needed for supporting communities. The hazard classification is shown in here. This figure is taken, I prepared this figure, and it was published in an ASCE document the document which is shown, the cover is shown in there, hazard resilient infrastructure. It's a classification that I followed the practice of classifying different hazards from geophysical to biological and so on, trying to provide a complete picture of the different hazards that we could encounter. And these hazards, they could be shown on the x-axis, as you see in here. This is the x-axis is the hazards, and I could have different sectors. And I'm listing in here critical infrastructure, and there are other sectors that you could add to this list, but this could be basically the systems that appear on the vertical axis and the y-axis. And certainly a class of systems which is not shown in here is natural and nature-based infrastructure, which is really is receiving a lot of interest nowadays because of the adaptation to the need to adapt for a changing climate. And the third axis in this figure is the adverse event cycle, because we go from preparation to event occurring, which will cause potentially damage, then recovery and so on, emergency response recovery, and planning for the next event and so on. So there is a cycle. So you have this three-dimensional plot, and our pursuit needs to examine different systems subjected to different hazards for different stages of the adverse cycle. And certainly we have risk and uncertainties in all of this. And the economics and geospatial, the location of the asset and so on within globally or within the US, all of these are considerations that will be needed to assess the resilience of the infrastructure, which will feed towards the resilience of a community. The core of the method that we put forward in the ASCE Manual of Practice on Hazard Resilient Infrastructure is in Chapter 2, and that's the flow chart taken from that document. The flow chart, I summarized it by this bulleted list. Start by defining the context which needed for defining the system, the level of detail of defining the system, as well as how the extent of coverage, scope, it could be in time, space, as well as resolution. And then the applicable hazards has to be identified, failure probability calculations, conditional probabilities in the form of fragility estimation, resilience assessment, which I will talk about in a minute. Then we'll get into the economics, exposure and loss analysis, loss accumulation, economic valuation if we are dealing with losses that needs to be monetized. Then risk quantification in the form of loss exceedance. Extremes, they have to be accounted for as a central item in here, extreme events. Uncertainty quantification in the estimates. Then options for enhancing resilience through resilience engineering and design. All the options, they have to be examined in a life cycle context, which will feed into benefit cost analysis to manage the risk. And then there's community socioeconomics, it can be considered. Chapter 2 is part of a sequence of chapters. I'm not planning to cover all the chapters, but chapter 1 is the context, chapter 2, which I just highlighted. Chapter 3, different methods for resilience assessment. 4 is on the economics. It was written by the chief economist at the National Institute of Standards and Technology, which is part of the Department of Commerce. Then engineering for the resilience, which was done by a couple of engineering firms in the US, in community socioeconomics. And then we have a very interesting chapter that is on emerging resilience enabling technologies. We had a review paper that came out last year in the ASCE ASME journal in this subject. And I have a few slides on what are those emerging resilience enabling technologies. The term technology is broadly defined as shown at the bottom in here. So it could mean materials, sensors, robots, cyber, methods, decision tools, handbooks, all of that is covered within technology. So these are all resilience enabling technologies. Let me point out before I move on to the next slide that this document, which came in 2021, was done or designed to be in line with a document that came out in 2018 with the title Climate Resilient Infrastructure that received a lot of attention in the US, by government and researchers and so on. The document, the 2021 document, was prepared by a team of about 21 people, and it went through a peer review process. It is the term manual of practice in ASCE terminology. It is a high-level document just below a standard. I think this area is not ready for standardization, but this is the highest level of document. Let me move on to quantification of resilience, which is the core of the document. Basically, it takes from the definition of resilience, which you might be familiar with. Resilience is defined as the ability to prepare for and adapt to a changing condition and withstand and recover rapidly after disruption. Or a more concise definition could be persistence of the functionality of a system. And that is really the resilience. One of the classic papers that came in the early 70s, which was in ecology, it defined resilience of an ecological system as the persistence of its functionality or its attributes. So in this case, we could say if I have a system, and it could be an infrastructure system that has a certain function, purpose, I'd like to define it so that that functionality will persist. So if there is an event, it will disrupt it, but it will come back, and so on. And that is the definition that we are adopting in here. So if I look at performance, which could be multidimensional, so I'm showing one-dimensional performance of a system, and I design it to be at some target on the y-axis in here, and I'm tracking it as a function of time. Certainly, because of aging, most systems they will degrade with time. Not all of them, but most of them. And if there is an event which is represented by this arrow, this event, which could follow a Poisson process, it could lead to failure or maybe no failure. But in this case, if I assume failure, so we have to calculate the probability of failure, which we know how to do that. The way it fails, it will follow a profile, we call it. That's the failure profile. It could be all the way from brittle to ductile to graceful. And then there is robustness, which is some residual performance. So it's not complete failure. Then there is some emergency response and recovery, rebuilding, and we could rebuild it to better than old or better than what it used to be as new, or any of those curves, and expedite the construction or rebuilding, or what. So we have many tracks that we could follow that are characterized in blue. Now, and then after that, aging will continue, and you'll have the curves which are shown in here. But if I want to quantify resilience, and we try to use concepts from theory of measurement and using measurement science to come up with a quantification of resilience, I'm going to offer two ways of quantifying resilience. One which is based on time, average time, and it's really inspired by the concept of availability. So I could say, well, resilience could be defined as basically the time to failure, which is the time to failure is the time when the system is functioning, divided by the total time, which is the time to failure plus time to repair. So it's TF divided by TF plus TR. But we have all of these performance levels, different F1 to F3 and R1 to R6. So how can I account for those? I could integrate under the curves and use some weighted scheme to come up with a resilience. So I could say, well, if a system will fail in a highly graceful manner and recover instantaneously, so as if you have a blip type of thing, then this will take care of it, and it will become available all the time. This could be a computer network where you could have backup systems, and they will kick in another, server or system that will take over if there is a problem in the one that was operating. So I mean, it's possible to design things to enhance resilience and allow for those failures. But the quantification is done still on the time axis with the integrals under the performance curve used in here as the deltas for weights. Now I could take time to failure, the T sub basically the time to failure T sub I or T sub F, which is up to here. I could model that by time-dependent reliability analysis, which is quite well established and so on. and actually this will become a random variable, then resilience will become a random variable. So all of these are add-ons that I'm not presenting in here. Just want to show you the track of thinking. The other approach is to look at it in a more simplified fashion, but it does cover, it has some limitation, but it does cover a lot of the elements that I mentioned earlier. So basically what we could do is look at, let's say, a planning horizon, which could be 50 years, 100 years for an infrastructure, or any time period T. So this is my planning horizon. And then performance is up to here by design. Let's ignore aging for now, although we could account for aging if we have an expression for the way its performance is degrading. But let's say with no aging, if there is an event if we have an event that will induce failure, then there is, and if I assume brittle failure, linear recovery, there is a loss of performance, which is represented by the area of this triangle. So I could say without this wedge that I'm losing, the total performance over its life, over its planning horizon, should be it's the area of the rectangle. It's T times Q100, and I could subtract from it this area if there is a failure. But this failure does not happen all the time, so there is a probability of failure that I need to account for, and I could have multiple of those throughout life. So I could basically take the one, resilience as one, which is normalized, and then subtract from it, depending on how many events I have, from one event to infinity, using the Poisson distribution, multiplied by the probability of failure, and then taking out those wedges, which are the failure, loss in performance in life. So I could quantify it that way. And there doesn't need to be this symbol shape of a triangle. It could be a step function, multi-step function. So it doesn't affect the formulation. It's designed to be almost modular by changing this R bar as basically the loss in resilience when there is a failure. Now this formulation could be simplified. So actually this infinite summation from series, mathematical series, you could show that this equation is nothing but this one. You could get rid of that series by using the exponential function, and you could write it in that form. So it will be 1 minus exponential minus lambda t, 1 minus p is the probability of failure if there is an event. R with the dash above it is that wedge of loss, which could be a step function or multi-step. It's the area of loss of this type. And the rest is all defined. Lambda is the event rate. So this model accounts for event rate, failure probability, initial and residual, robustness, duration of the disruption, planning horizon, recovery profile. All of that is covered in there. And if I consider the planning horizon to be the same as the return period, which is typically the case, I could actually simplify that equation to this form. So this form, and if you plot it in parametrically, assuming robustness to be 25% of the performance and a recovery period, we are using this case, a triangle, brittle with linear recovery, and I'm assuming a recovery period from 1, 5, 10. I mean, you could parametrically and change the failure probability from 0.001 to 1. You could show how resilience vary by the use of this equation. Now, let me focus on performance. What is this performance? Performance really depends on the system. So I have a table in here that gives you different systems and examples of performance. So if I use roadways, you could look at throughput traffic, which is typically, that's what we measure for bridges and roadways, is how many vehicles per day. So you could say, well, this could be one dimension of performance for a roadway. If I consider, let's say, a coastal protection by vegetation and dunes, natural system, you could say, well, what is performance of a dune, right? I have some examples on that, so I'll save that for later on. If for a community as a whole, if you have a city and you'd like to know, well, what is the performance of a city before and after an event, after a hurricane, before a hurricane and after a storm? It could be basically the well-being of the community. Well, how can I measure the well-being of a community? In a roadway, we have counts of cars. Well-being of a community is really an aggregate of many things. They need to have the power system working, the transportation, schools, healthcare, foods, and so on, water distribution, and so on. So we look for a method for measuring, or a unit of measurement that will be suitable for a community. I call it as an integrator of all of the above systems. And the best integrator is really economics, because in order for a community to produce economic output, all of these systems, they have to be functioning. So you could really measure it in two ways, either economic output or consumption level. Most of the time, economists, they prefer economic output. So we could say, well, the economic output of a community is a measure of the well-being, and it's a measure of the recovery or the performance of the system. And I'll show you an example of this later on. Let me give you an example about water distribution, just to show you the multi-dimensionality of performance when it comes to one of those systems. All of them, they have multi-dimensions. So water distribution, this is based on the work that was done at the LA district, which is the largest water distribution maybe in the US. That one, the multi-dimensions of water distribution is the top one, the top performance item of concern to the LA district is water availability for fire. So fire hydrant, because if there is an earthquake and so on, you could have more damages due to the fire than the earthquake itself. So one of the things they track is the water availability in the fire hydrant. The second one is water availability for consumption, quality of water. I mean, this could be volume or quality. Then the next measure could be reliability of the system, right? Because the system consists of pumps and valves and so on. So you could look at the mechanical reliability of the system. So it's multidimensional. So all the systems are multidimensional, although I show a single dimension, but I'd like you to know it is multidimensional. Let me look at underground spaces, which is an area of interest to me in terms of resilience of underground spaces. So if you look at underground spaces, I took this from an Australian publication, which is cited at the bottom. The context in here is civilian use. Certainly there is big military use for underground spaces, but in here you could look at by depth that there are pedestrian utilities, which tend to be relatively shallow, 1 meter to 3 meter. Then you have pipelines, which could be 1 to 10. Then you have transit and cars, metro, and so on. And then you could have deeper utilities such as sewage lines and so on. And then you could have industrial and storage and military and so on, which is even deeper than that. So these are the underground spaces. Now, if I'm interested in performance, I need to maybe to understand the performance of those systems, I need to maybe reflect on the hazards. So basically, I looked at the hazard hierarchy that I showed you earlier, and we could examine each one of them. Earthquakes, yeah, it does affect it. Volcanoes and so on, mass movement and so on. I mean, there are many hazards that could disrupt this, right? And the question also, you have interactions. I could call them compounded hazards. So you could have a climate change, which will lead to water intrusion, which could lead to sinkhole, which could lead to flooding, and so on. So you have some complex interactions that could happen. Let me show you an example of an underground space, which is New York East Side ASCE project. This project is 40 miles of tunneling, which is expanding on a system. The metro system in New York is one of the earliest, in the US, started in 1871. So it's an old system. And basically, this is a very ambitious project that was in the plans from the 60s, but it was revived and so on in the 90s, dug up in this period, 2007 to 11, and then expected completion in this year, $12 billion. It takes you from Manhattan, from Park Avenue to East Side. And basically there is multi-level tunnels. Some of the tunnels, the green line, which crossed the river, actually they put the tunnels long time ago in the 60s, but they were never used. So they were using those. And then these are the red and the blue. They are the new tunnels with underground spaces for shopping and retail and so on. It's a sizable project. I have a video on it, but I don't know if we have the time for it. But the tunneling, you could see some of the pictures in here. It's multi-level. It is I think like you have 10 stories below, 14 stories below ground, 350,000 square feet, and so on. So it's quite sizable. And basically, if I want to look at the hazards and come up with a list of what's applicable in here, I could say, well, there is, and what's the performance? I could say, well, one key performance item is the geometry. I would like to maintain that geometry, because if I have a circle as a tunnel and there is a train that goes in it, tolerances are key and important. And if it becomes distorted due to earth pressure, which could happen, and that actually based on real cases, it could become problematic. Water intrusion, anything underground, you'll worry about the water. You could have it the other way around, content leakage, because some of those pipes you could be carrying, water or gas and so on. Corrosion, deterioration, animals, is a major concern, especially in shallow tunnels, utility lines and so on. Underground cavity, sinkholes and so on, which is driven by water, depending on the geology and so on. Cracks, fracture, and so on. I'm not planning to read through all of them, but these are different type of hazards that we need to worry about. One of the, in a project that we did on the Shanghai Metro, we looked at collaborating with Tongji University, and some of the names are shown in here, they use segmental construction. So this cross section is made out of 5 segments. It's actually modular, the cross section, and it's done in segments longitudinally as well. And there was distortion as a result of buildup of the city. So a measure of performance was the level of distortion, and they used grout to try and recover the geometry, to pump grout. We did some testing a couple of years ago. We just published this work about if you have a modular cross section and then you apply loading on it, how does it distort? And if you apply through simulation, if we apply the pressures, can we really recover from it? And then there were sensors that were put in place and so on. And all of this was put in the form of resilience representation, like what I showed you earlier. Now, when it comes to resilience quantification, sometimes people like to look at what they call the 4 Rs, resourcefulness, which comes before the event, you build up capacity, enhance the system, robustness, which is residual performance, redundancy, which will basically alternate load paths that will help in terms of maintaining some of the robustness. Then rapidity, which has to do with the rate of recovery, the slope of this curve. The reason this fine breakdown, because actually you could create technologies for different pieces of it. And that's what was done by Professor Taha, who does a lot of technology related to resilience at the materials levels and sensors and so on. And all of it, you need to look at it in the form of quantification, measurement, and of course, economics and trade-offs will play a major role. Let me show you how we will bring everything together for economic analysis. A key item is loss accumulation, which happens due to failure and the cost of recovery. And then if we take an action, the reduction in the loss accumulation will become the benefit. So a key building block is really loss accumulation. But we need to tie it to performance. In the water distribution example of LA that I shared with you earlier, these are the fire protection, the quality, the operability, which is the reliability of the system, and so on, the delivery of. So you could actually track the resilience curve according in multi dimensions, and that's what was done in here. Data is a challenge because you could have actuarial data for some cases. Some will be based on published results, some engineering judgment, and some by expert opinion. So we need to quantify the uncertainties because of the reliability of the information that we have will vary. And then in what we did, we built a loss accumulation model, which is shown in this equation. And it's really, it's a simple equation. What you have here is an event, which is basically it leads to some hazard, which leads to failures. Everything is conditional. You are following the branches of a tree until you get to loss, the L. So you are multiplying basically probabilities, and at the very end there is the loss, which could be a random variable. So you could get loss accumulation value at the very end, and the exponential term at the very end in here has to do with a discount rate using time value of money. And if we have the loss computed, and this could be done over the life cycle of a system, and within we implement an action, I could determine the loss reduction as the benefit and define it divided by the cost of the action. So this will give me the benefit to cost ratio, but I could treat that probabilistically to compute the probability that the benefit will not be realized. And we tend to do that. I like to do a probabilistic treatment of the benefit to cost ratio. Most of the time people deal with it as a deterministic quantity, but I don't think it reflects reality. Most of the time, the benefit, we have a lot of uncertainties in it because we are doing projection over time. We are dealing with, rare events and things of this type. This slide has to do with the technologies that Professor Taha and we collaborated on this, just trying to map it by the 4 Rs, from smart materials to basically sensors, robots, as well as the maturity of the technology, which is represented by this curve, and different data analytics that are described in here, which could be all the way from the sensor level to the way dealing with cities and so on. So this slide has a lot of content in it, but I don't have the time to go through all the details of it. I want to bring it to your attention. One of the key items when it comes to resilience is recovery. I have a couple of slides on recovery. The first slide, which is about a bridge that collapsed in 2007. It was on Interstate 35 West, which is crosses the Mississippi River. I drove across that bridge many times over the years. It's near Minneapolis in Minnesota. And it was catastrophic failure leading to 13 deaths and 145 people injured. Most likely the people think it was fatigue failure of metal fatigue. The system was not really redundant. This is the new bridge that was made out of concrete and so on. Basically it took 1 year, disrupted traffic, which is 140,000 vehicles per day traffic, daily traffic. So it's a high volume bridge. It resulted in people going through a lot of delays and so on. But the message of this, the recovery profile, you remember the recovery profiles, R1 to R6? This one is a step function recovery profile. So there is no bridge for a year, then a bridge is back, right? So that's just gives you an idea about the recovery profile. The other example is basically Hurricane Katrina. In this case, we have this event happened in 2005. It affected the city of New Orleans. If I look at the city of New Orleans, if I draw a cross section from point A to point B, and the city is located over here, that's what you'll see. So it is a city which is below sea level. On one end, there is the Mississippi River, which is this river in here. On the other end, we have the Gulf, which is part of the Atlantic Ocean, the Gulf of Mexico. And the hurricane came with this path. You could see it crossed over Florida, then built up speed and strength, and then landed near the city, leading to a flooding, quite devastating the city, flooded an area as big as the UK, resulting into $40 billion in damages, and even more in terms of reconstruction, $120 billion in reconstruction. Keep in mind, these are dollars of 2005. And you could see some of the images from flooding. I was the lead risk analyst. The big questions that was given to us is at what level we should be protecting the city. If I want to build the flood walls and the levees that were failed, to what elevation we should do that. And I can tell you that you cannot protect that city 100%. So at the most, I think the protection was I'll say, between category 3 and 4 in terms of hurricane intensity. So if we have a hurricane of 4 and 5, it will end up causing the same problem. The city is below sea level. That is a risk that we have to live with. But the recovery, if I want to look at the city recovery, how can I deal with recovery in here? What is recovery? What is the performance of the city? And I mentioned performance of a community earlier. I said it's the well-being of the community. It's economic output. So we looked at it in the form of economic output. So we had GDP tracked from 2001. The blue curve is the US and the gray is New Orleans. They were indexed or pinned at 100 in the year 2001. And these values are reported annually. So it doesn't have the resolution on the time axis to show you when the event happened, how we have a sudden drop, because it's done annually. So you could see that the gray curve, the New Orleans was actually performing better than national values until the event which happened in 2005, then it dropped. Of course, it was a sudden drop, but here again, it's not reflected because of the values reported on an annual basis. But there was a drop, then it continued to drop, then it starts to build up and eventually started to build up, catching up and exceeding the US economy, GDP for the US. But the point in here, what is recovery? Did we recover? I mean, if you look at it from economics, you could say, well, yeah, this was higher than the national, but the whole national economy is changing, right? And the city, when it recovers, it's not necessarily it's recovering to what it used to be. I mean, many businesses moved out, people did not come back, and so on, and some other industries moved in, and things of this type. So it's a very dynamic system. So we could say the recovery is maybe this much, 8 years. So yeah, it recovered, took 8 years to recover. But recovery is really complex, multidimensional. There is transfer from one city to another, disruption. There are many aspects to it. In fact, the city, if you look at it by population, by size, it did not recover to the population before the event. Before the event, it had a population of about 1 million people, and at the present, I think it's maybe 700,000. But the economic output is at the same level at what used to be. So the mix of industry, the mix of population is different. It's almost having slightly different city after the event. Let me move on to the next item, network and infrastructure. I have too many slides on this, so maybe I'll try. What we did is we took the tunnels work and we were interested in the transportation systems that are affected by, or rely on the tunnels. So we use complex network theory. A network is defined by points that or vertices and edges, which are the links of the lines. In the case of a metro system, if I choose this example, the stations will become the points or the nodes, and the links will be the rails between the stations. I have other examples in here, but if I focus on the metro system as well as railroads, when we have a network, it's very common that we build what's called an adjacency matrix. All it's showing you between each pair of nodes, I and J, if they are connected, there is 1. If they are not connected, there is a 0. So it gives you connectivity. So based on this, I could have an adjacency matrix of this type, which is commonly, that's what we have. Although if you have multiple connections, which is rare in transportation, you could have more than one. You could use weighted network. If you could attach, instead of having one, you could maybe attach higher weight to certain links than other links. So we could have weighted network. It is symmetric if those links do not have directionality. If they have directionality, it will not be symmetric. We could put the network, the nodes in groups and define what's called hypergraph, which we're not going to do in here. Now, each node is connected to other nodes. So how many, the number of nodes is connected to is called the node degree. So we could calculate for the network an average node degree, and then calculate how many links do I need to go from node I to node J, how many links, just counting links. And that's called the geodesic path, and determine the shortest path. And there is algorithms for calculating that. And then from it, I could calculate the diameter of the network, which is the average path to travel from any node to any node, and then use it as a basis for calculating the network efficiency, where the efficiency becomes 1 if every node is directly connected to every other node, and it degrades from there if the network is not fully connected, which is the case most of the time in transportation systems. Now, I could take that network efficiency and attach weight factors, which is what we have in here, along the travel from I to J, just sum up those weight factors, or it could be unweighted, and use that as the performance for dealing with resilience, like in the previous curves. And that's what we did. And we started with work in Shanghai Metro. The map, which with the animation is showing the development of the metro systems in China. And Shanghai Metro has about 300 stations. It's the largest in China. And it's almost half the size of the one in New York, 3 times the size of the metro system in DC. So what we did, we examined the tunnels, which I showed you those. We looked at the metro system in both Shanghai and DC. And the hazard that we focused on is flooding due to water level increase as a result of surges. And this is driven by changing climate. Both Shanghai and Washington, DC, they have the topography, the elevation, they are similar. Both of them are vulnerable to flooding. It's almost similar to London. There is, if you have a surge of a couple of meters, it could end up leading to flooding some of the stations. So basically, we took both systems, discretized it in the form of a network, and we examined projections for Shanghai in terms of sea level rise and how it will translate to surges. And we basically looked at the network, and these are all the nodes, and the links, we defined them as well, as you could see in here. Then we examined the loss of each node one at a time, and to what extent it will disrupt the network in the form of the efficiency, and if identified Century Avenue station as being the most impactful station. The loss of it will disrupt the network the most, and so on. And then we examined the recovery sequences. So if I have a station that's impacted, which line should I connect first, and what's the sequence? This was driven by economics. We examined the elevation of these stations. This histogram shows how many stations, the count by elevation. We took actual measurements. We had a team of students worked on this. Then as the water level was increasing, you'll be able to see how many stations would be flooded and their locations. Washington, DC was treated similarly. There was node 38 was identified as the most impactful node. Most of the time they are hub nodes, which you expect that. We again looked at the flooding of the city. You could see Washington, DC in here. The White House is somewhere over here. This is the White House. That's the US Capitol and the monument, and the flooding as you increase the water level. And this is the economics of it, the loss accumulation. This does not account for underground systems. We did not have the information on it. It accounts for residential houses, businesses. As the water level goes up, what's the total loss, assessed value of the total loss. Railroads, this is an ongoing project, so I just want to show you a few slides. The panel on this side shows the ownership. There are 7 key players, companies. This panel, the size of the line shows the volume. And basically what we did, we came up with this network as the network is very complex in the US. We had 140,000 miles of rails, 140,000 miles of rails, right? 40,000 stations and waypoints and so on. So we simplified it to 100 nodes. We called it an aggregate network. It's not a real network, but it represents realistically, the shape and the structure of the network the way we have it. We had 226 links. We tied it to counties because a lot of the reporting is done at the county level in terms of goods moved. So each node is like this blue area, this green area it feeds into node 17. So we basically associated all the counties. There are 3,100 something counties. We link them to nodes, associate them to nodes, and these are the links defined in here. So from that, we're able to calculate which nodes are the most critical ones and which links are the most critical ones in terms of impacting the whole network. So these are the top 5 basically critical nodes, and these are the top 5 critical links using basically weighted and unweighted. We analyzed it both ways, and then we examined the role of interchanged goods. The weights are volume of goods. Volume of goods are looked at by origination, termination, and what we call interchange. Interchange is when you shift it from one, it goes to a node, but it's not the final destination. So we examined the effect of the interchange. It didn't really play a major role. Nature and nature-based solutions, we did a study for the Army Corps for protecting coastal areas. We used a resilience formulation for it. Basically, these are the type of systems we are looking at for coastal areas. And the question for us was, what is performance? So we came up with, the document looks at performance of those systems. The dune height, the vegetation type, the density of vegetation. We examined the resilience, the performance profile as a function of time. Sometimes you leave it to nature to nourish the system back after erosion and so on, which is a slow process, which could lead, you might have another event before it's fully recovered, right? So it might require intervention of the society or the government to actually build it back if we can't rely on the natural process. The adverse event cycle is unique in here, which is covered in this chart. You remember that 3D plot I showed you at the beginning? The economics,
Sorry,
failure.
just a reminder that it's 45 minutes, but just a general reminder, I know you still have some more time to wrap up.
Okay, well, let me wrap it up. So this is the economics of resilience, basically the benefit to cost analysis. I think I covered some of that, but basically the color coding, this is the cost of failure, the cost of recovery, the cost of loss of use, and we put it in some economic framework. The last slide I have is on socioeconomics. Socioeconomics, you have to do it at the GDP level. So basically you'll say, well, you have some economy in some country. This could be done at the country level. So you have some economy, or it could be a region. And if there is an event, it will shrink the economy. Some local income will reduce. Transfers, they tend to be maybe not affected, not as much, by the way, because the income was coming from other sources. And that's called welfare loss. So I could actually recover some of the welfare loss if I have programs, insurance and things of this type built in. And at the very end, through welfare support, we call it. So at the very end, I could take the welfare loss, which is non-recoverable. And if I take the total asset loss divided by the welfare loss, that ratio by economists, they call it socioeconomic resilience. And this map shows color coding of that ratio. So the darker, the worse it is. And it's certainly related to GDP per capita. If in this figure, if you map socioeconomic resilience versus GDP per capita, you'll find there is some correlation, but there is a lot of scatter in it. With that, I'm done. So this is just my concluding remarks. I summarized, what we are doing in hazard resilient infrastructure for supporting community resilience. We looked at technologies, economics, and socioeconomics, and these are some sources that you might find useful. And thank you for your attention. I'm happy to take any questions that you might have.
Thank you, Professor Ayyub, for a really wonderful talk, really interesting. I took loads of notes. Yeah, really, really intriguing and interdisciplinary. So yeah, thank you for sharing your work. I do have a few questions, but first I'll just open up the floor to see whether anyone else would like to start off. If you do have any questions, please feel free to unmute yourself. And if not, I'll begin. So I have two questions. Excuse me if they're a little bit naive. There was one slide at the beginning when you were talking about the interconnectedness of risks, which I thought was really interesting, and the diagram that you presented there. Was that your own diagram?
Yes, that is my own diagram. And basically what we have the different hazards, they are interconnected. Sometimes you have, what you might end up having is a compound hazard because it's coming, because one hazard type generated another form of hazard, and the two together will end up creating a situation which is worse than treating each one separately.
Yeah, no, I really liked that. And I was just wondering whether I could potentially do something similar and what program you use to program or to create that graphic.
Oh, that graphic? You mean the color coded? See the graphic that shows the different hazards.
Yeah, connected, and they had hazards. You could see the ones that were slightly bigger because they had more emphasis, and it was kind of like a grid almost. There were lines connecting them all together.
Yeah, this one I used. I think maybe I used Visio for creating it.
Visio. Yeah, thank you. Because I think I might try and do something similar for a piece of work. So that was quite inspiring for me.
Sure.
And secondly, when you were computing the probability of failure, we were talking about resilience quantification. I was just wondering how you compute the probability of failure for a larger system when you say it was either a business or a company, a factory. How would you go about computing that kind of probability of failure?
Well, let's see, calculating the probability of failure would require first defining what is performance. So if you have a system, we need to understand and clearly define in measurable fashion what is the performance of that system, whether it's a business or infrastructure system, cyber system, whatever it is. I think the challenge, I'll find it always, the key item is really defining performance. What is the output that you care the most about? If sometimes it's not easy, it's not obvious. And the way you could make it maybe clearer, if you ask a question that if there is after an event, and if I come and examine that system, what do I worry about? What's the item that I would like to recover for that system? And that's what most of the time, the item that receives the attention for recovery is the performance that I should be tracking. So let me give you an example. When we're doing the work on what is the performance of a dune, right? How can I measure the performance of a dune in a natural system? Then I asked, the engineers who deal with it, they manage the coastal areas and so on. After a hurricane, what do you try to do to fix those dunes? They said, we'll try to beef up their heights and enhance the vegetation. So I'm all right. Well, the performance is the height and the vegetation density. Just these are the items that we should be focusing on, and these are the ones we should track, and these are the ones we need to enhance before the event and get them ready, right?
Yeah.
Does that help?
Yeah, no, it does. Yeah, thank you. That is interesting. And just really appreciated the discussion around the well-being of the community and how you go about tracking that. I thought that was quite fascinating. Yeah, thank you. Does anyone else have any questions?
Francis, can I ask you a question, please?
Sure.
Okay, Bilal, firstly, it's such a fascinating talk. I have thoroughly enjoyed. You've given us so many topics, so many research results. Of course, it takes time to digest. But one question I want to ask you is the definition for resilience. Okay. For probably the last 20 years, resilience has been a very hot topic, as you know. And in many conferences, people have been arguing as to whether the resilience can be quantified. There haven't been any agreed quantification models for resilience. But early on, I noticed that you defined resilience using a formula, which is 1 minus the weighted areas in terms of reduced performance and the timeline, something like that, which is quite interesting. I wonder the definition you have shown to us is something that has been verified or taken up by others? That's something I have a strong interest in.
No, I think the quantification of resilience is an area of active research, right? And you certainly, when you measure something, it is a convention as opposed to something that you could verify. I'm maybe talking in a fundamental level in here. So if I want to measure, let's say, likelihood, which is something that we do all the time, the accepted way of measuring likelihood is probability theory, right? Can I verify probability theory? I mean, is probability, it's a construct. It's a system of measurement, right? We have axioms for it. We assume that probability is between 0 and 1. We set some axioms, right? We consider that I need to know the sample space. The universal set is known to me because one of the axioms is the probability of the universal set is equal to 1, right? So I created a construct, and that construct, which was, I didn't create it, but mathematicians created that construct, which stayed with us now for hundreds of years, and it works, right? Resilience is the same thing. So what I did in a paper in 2015, I really used principles of measurement science. I said, okay, I'm trying to measure resilience. What are the axioms that I must have, right? So I built it up almost being inspired by the way probability theory was constructed to measure likelihood or chance, right? So probability theory, if I define what is probability is a measure of likelihood, right? So in here, we have a measure, which is an equation or a model of resilience, but it's a construct. It has the foundation, I'll say, and it's being used. And actually, the citation of that paper, the 2015 paper, is very, very high, and it's being used by manuals of practice in ASCE and so on. And it's not a far departure from some of the work that was done in 2007 in measuring resilience. And it's not far removed from the concept that was developed in ecology in the 70s, which is one of the classic papers in resilience of ecological systems. So if my logic in simple terms, I thought, okay, if you have a system and you have a planning horizon of 50 years, and you have on the vertical axis some performance you expect, that rectangle is what you expect from it. That's what, you're putting that system in place for 50 years to give you so much performance, and you want that area. If you lose from it anything, then that loss, you could make it less by making it more robust. You could make rapidity better by making the slope bigger, and so on. All you are trying to do is reduce those wedges, those areas that we lose because of events. So if I could basically calculate that in dimensionless manner, so I divide, normalize, so it's 1, right? I could come up with a measure for resilience.
Yeah, absolutely. I think I agree with you. I think I'll probably read your 2015 paper in a little bit more detail, then try to understand it better. But it's very useful. I mean, I agree with you. It makes a lot of sense, quantification of resilience. By the way, you work with Mohammed Madris at Maryland Center for Risk and Reliability, right?
Oh yeah, sure. Yeah. I mean,
and also, I believe Ali Mosley used to be your colleague as well back to some years ago.
That's right. Yeah. I mean, both of them are my colleagues. Yeah, Ali Mosley, he's at UCLA now.
Yeah, I know.
That's right. Yeah. And Mudaris, he's still Professor Mudaris. He's my colleague.
Oh, excellent. So I will be very in touch in the future. Good to listen to you. But I really need to go now because I have another meeting to catch.
Oh, sure. Good to meet you. Thank you for your comments.
Meet you here, Bilal.
Thank you for coming in your questions. We also have knowledge work. I'm not sure who his name is.
Sorry, that's Scott Person. It was a joke to put that name on there, and now I can't get it out. So sorry, I missed the very beginning of your talk, Bilal. I apologize. I was desperately trying to do something. I like Professor Wang. I'm very excited by this talk. The whole idea is very interesting. I assume by the ecologists in the 70s, you mean like Buzz Hulling and Richard Levins, those guys. Is that
that's right?
So
yes,
that's actually my background, as a matter of fact. So I'm interested. I was going to ask you the question whether you think that this theory, that the conventions that you've constructed, that are a full picture of resilience, but maybe the better question is, what do you think we need to do next to build on this theory of resilience? I mean, you know, there are a whole bunch of confusing issues like qualities and you know, and how exactly we determine what the dimensions of concern are and so forth. So what do you think we need to do next in terms of building a theory that's going to be as useful to Professor Wang and the others as they need?
I think, you know, defining, I mean, you did identify a key item is defining resilience requires defining performance, right? Or the functions. I mean, you know, if you look at the classic definitions and the classic work, always it's tied to some persistence of functionality. So, and functionality could be, it can be measured by some performance, because I'd like to quantify it somehow. So defining those dimensions can be challenging, right? And it's not just defining them, because examining each one separately might not give us the answer at the very end, because they are interconnected. So understanding the way they affect each other, I think is challenging. The other item, which is I think is quite a challenge, is aggregation. Because if I have, it's almost like systems reliability. If I know the resilience of different components, how can I get the resilience of a system that depends on all of these components? So resilience aggregation, there isn't much work in there in terms of how to aggregate. There are some basic models that are all inspired by systems in series and systems in parallel, but I think it's much more complex than that. So there is a need for work in that area.
Talking about the inputs. Are you talking about the inputs then to a system?
I mean, it could be, well, let me maybe give an example. So let's say if I'm looking at the resilience of a community, and the community resilience depends on the infrastructure resilience. Assessing the community resilience based on assessed infrastructure resilience is non-trivial. So the aggregation, if I know the resilience of the transportation system, I know the resilience of the, I quantified it, and I'm quantifying them, let's say, consistently. Resilience of transportation, resilience of power, resilience of telecommunication, resilience of food distribution, and so on. How can I aggregate all of that to assess the resilience of a community?
Okay.
So that is, it's problematic. So I think what I found that it's easier sometimes, instead of analytically combine them, it's easier to find a different performance measure, which could be economic output. I consider it to be a higher level integrator, right? So instead of doing aggregation, sometimes I favor doing an integral, right? So I'll find a different measure that's actually does require all of the above for that measure to give me the value that I need. Economic output is one of them. So you could say, well, economic output will require, you know, the roads, the water, the food, and so on. So selecting those performance measures, I'll say some of them could be at the fundamental level. They are addressing a system individually, but some other measures could be more of an aggregator.
Right.
Not aggregator, I'm sorry, integrator.
Right.
Aggregation is when you sum up the pieces, but we can't figure out the logic, how to sum up those pieces. An integrator is an item, it's a measure, it's a new dimension, such as economic output, which accounts for all of these things. So sometimes, go ahead.
Sorry, I get excited. I mean, another notion that's popular in biology is this notion of what they call biotic indices, which are basically ways of measuring systems that aren't necessarily obvious, but try to integrate the components that are of importance. And those are starting to emerge in other disciplines too. I noticed in economics, for instance, they talk about I guess Tibet or someplace measures the happiness index of the nation rather than the GDP. And that's, in theory, you could do that, right? And in other places, there's a goodness measure of all the countries, and you can find the goodest country. It's not the best country, it's the goodest in some sense that integrates the various, external foreign aid and taking care of their own people are integrated into some essentially a biotic index of the nature or the quality of this country in some economic, some sociological sense. So what do you think about these indices, which to my mind seem all kind of made up? Are they acceptable to you? Or do you think that they need to be, are you sort of, let's get down to the money? Or do you think there needs to be something that's more clearly quantifiable? What do you think about these sort of homemade things?
I think, when it comes to measurement science, all of it is what I was saying earlier. It's all a construct, right? Yeah. If we are dealing with notions and notions that are not physical, right? I mean, if I'm dealing with distance or weight and something of this type, the measure, maybe it will not be an item of that needs to be debated. But if I'm dealing with a notion which is a fragment of our imagination to some extent, right? I mean, happiness and things of this type. Yeah, I mean, those will never get to a stage where I have a solid, 100% solid foundation that I could say this is the measure. I think a key item, if I want to assess how good the measure is, if I want to have a measure for assessing the measure, right? How good of a measure do I have? How good of an index or a measure do I have? The way I could assess it, does it enable me for making intelligent decisions? Because at the very end, it's about decision making, right? And decision making is driven by some criteria, which is anchored by some value system, right? So I could say, in this case, economic valuation could become, a major item. I mean, you could bring in the markets and the economics and say, well, if I use happiness as the index, right? I'm trying to enhance my infrastructure systems and so on to enhance happiness, right? And there are people who try to measure happiness. Does that lend itself for economics, microeconomics? Because at the very end, I need to allocate resources. So I have to bring it to a framework where things are unit consistent. So if I'm spending money, I'd like to know how much return I'm getting in terms of money. So I could say, well, all right, can I translate that happiness index to some? Is there a market for it that I could actually figure out the trade-offs? So I think the challenge is going to be. I mean, you can go to more fundamental level in ecology, and that's your area. People struggled with that. I mean, what is the economic value of an item, especially if it doesn't have a utility now and so on, and it doesn't have a market now. How can I attach a value to it? So economic valuation could become, and again, it becomes, is it anthropocentric? Am I dealing value to humans or value to what? And so, I mean, there are the ethics and the values, and there is a lot of complexities to it. It's all recognized, but I'm not giving you an answer one way or another. But I think at the very end, I'll say, if I want to sum up what I just said, is it helpful for making intelligent decisions, right? If the answer is yes, yeah, I'll favor it. Would it make the decision-making better, more intelligent? But then, value system will kick in. Intelligent in what way? Intelligent to individual? Is it a policy session where I'm trying to set a policy for the whole city or country, which will affect everybody? Am I looking at it globally in terms of impact on the environment and people and so on? And so, I mean, the value system will become really, it can easily become a challenge in that regard.
Thanks very much.
Thank you. Very good question. It just I don't have the answer for those. It's a very hard one. I mean, we are dealing with it. We organized recently a workshop for the Fish and Wildlife Service. They have national refuges that they have to manage, and the question was impact of a changing climate. And they know that those national refuges are being devastated, and they can't do anything about it. You cannot protect them. You can't build, flood walls and things of this type. And the question is really a managed retreat, right? So how can I affect the process to get a system, if I could affect it actually, in the future, which will have the mix of the wildlife and the environment and so on, that will be most beneficial. Measurement is the foundation of all of it, and there isn't a clear answer yet.
Yeah.
Thanks.
I
welcome any ideas you might have, Scott, on this.
well,
your area.
Well, measuring the unmeasurable is a particular interest, right? And I guess I'm a logical positivist, like all engineers are, and we think that the world is put together with things that appear in metric units. But our sociologist friends or the psychologist friends, they say, oh, I can measure honor or honesty or beauty. I can measure all of those things, and they have no problems, trotting out these things which they call measurements that to us, I think, feel a little foreign or forced. And I'm very curious as to, you're suggesting that it's practicality that determines whether or not a measurement is useful, whether it makes us more comfortable, I guess, with our decisions.
That's right. Yeah.
But I think, it's also possible that we might be just deluding ourselves.
It could be, of course, yeah.
We measured beauty in the United States for many decades with those beauty pageants, and look what that got us. So it's not clear that measuring the unmeasurable is I don't know. It's very exciting. It's very interesting.
Well, the thing is, I think what makes it difficult is it really absolute measurement or is it relative, right? It has to be relative, right? Relative to the person who's doing the measurement, right?
Yeah, subjective, right? Yeah,
it's subjective, yeah. So it's not that absolute measurement, right? So I think it changes with time. It's evolutionary to some extent, right?
Yeah.
But I think I'll come back to maybe what I said earlier, that maybe we are engineers and we have a code of ethics, and we are inclined towards solving problems, and the way we solve problems by decision making. Would like to enhance the well-being of the society and produce products and services for that purpose. And ASCE, they have their ethics code, and ASME, and many societies of this type. So I think if you tie it to decision making and better decisions, intelligent decisions, it doesn't give the final answer to it. Still, there is subjectivity left in there, but I'm not sure if we can pull out the subjectivity totally from it.
Mm-hmm. It's very, very interesting. Thanks.
Thank you.
Yeah, thanks. I was quite interested by that as well. I've always thought that the GDP is the wrong thing to be measuring the performance of the system, personally. I was quite interested in I think we called genuine progress indicator, Scott, the thing that incorporates happiness, and also the fact that an oil spill, for example, is somehow considered a positive thing in economic growth because the money spent cleaning it up is growth, right? Which seems a bit counterintuitive there. It definitely feels like the wrong thing to be measuring
and there are some classical crazy ideas. For instance, the people who talk about economic valuation of the biota of the earth. And a few years ago, it was before 2015, but someone came up with a total dollar amount for how much all the earth's biota, including humans, cost. As if someone like Tesla owner could buy it. It was terrifying in a certain sense, right?
That's right. I mean, economics, it has a limit of how far you could take it. But the problem is when you work with economists who will end up at the very end. I mean, engineers are not really the decision makers. They feed information to a planner or an economist and so on. At the very end, you will find that they will pull in those economic measures. And that's what will, I mean, we kept away from that process. Sometimes we are engaged in it, but I mean, I worked over the years with economists, and I tell you, it's all about the national economy. And in the work of Katrina, they wanted to consider indirect losses, right? So the direct losses were easy to deal with. They looked at property damage, they looked at life loss. There were maybe 1,200 people died and injuries and so on. They were able to add up all the losses. We have 12 economists involved in the project. It was a sizable undertaking. The indirect losses, they could not handle. They could not deal with substitution, the global economy, how one industry is devastated will end up leading to another industry rising up, how Houston economy was enhanced because of New Orleans economy declined and things of this. I mean, the minute you open up the box a little bit or the zone, and even they stayed national, the minute you open it up to the way the world is interconnected, many of these economic models, I think they will reach their limits.
Yeah.
So there are deficiencies. So at the end of the day, the 12 economists who were involved, they said we are limiting the economic analysis to direct damages and life loss. Indirect losses were not counted for. It seems we have something on the chat here.
Yeah, I saw that. I don't know whether it's necessarily a question, but Marco comments, I wonder how much qualitative models can do for decision-making of such large multidisciplinary systems. I don't know whether you have
Interestingly, the ecologists that developed this theory of resilience for ecology were the same ones who argued for qualitative modeling. So that's could be a pointed question in a sense.
I mean, qualitative modeling, you could, there is room for it, but I'm not sure that the limitations, I could say, or some of the limitations could be, is it scalable within a system as well as across systems for consistency? Because when you deal with resource allocation, I mean, as you go up in the decision-making or policy-making process, then people will be comparing across systems. So qualitative, I think the key item in there, I'm not against qualitative models. I think qualitative models, they could maybe do the job. The key item for me is consistency. In fact, when I engaged in with some agencies where they wanted to use qualitative models for various reasons, I was totally fine with it, but I thought it has to be consistent with OMB practices and practices where you would go and seek the funding, as long as it could make the tie with it and is consistent with it and it can support the case. I'm not in favor of any complex methods just for the sake of complexity. So qualitative models might work, but they will be designed for a particular purpose. But I think somebody should examine, are they scalable? Are they consistent with other practices that are accepted? And vice versa. I mean, if somebody coming up with a quantitative model, they have to look at it in the same way.
That's a good point.
Consistency, I think, is the key. I mean, we were doing in the wildlife, Fish and Wildlife Service effort, they wanted to screen all the refuges to identify which ones are the most critical ones and so on. And I argued for looking at first coming up with a thoughtful method that lend itself for quantification to come up with a screening method from it. So the screening method will become consistent with a future detailed method that once we do the screening, we'll have a short list, then we need to analyze to figure out what we should do. So consistency, I think, is important to be maintained between qualitative, quantitative, high-level screening to detailed analysis. They have to come together at the very end. They have to feed in each other.
So I was confused by the beginning of your response. So they suggested that they should do screening, but you agreed with them that the screening is important as long as it's consistent.
That's right. The screening is important. Yeah, I mean, in the safety of dams, we did a program over multiple years in the area of safety of dams. The Army Corps was faced with a similar situation. They had many dams that they have to deal with, and they cannot analyze them in detail to figure out which one they should, enhance safety. So we come up with a screening method, but we made sure that the screening method is in agreement or aligned or properly structured with a full probabilistic risk analysis method in the key elements, right? So we'll make sure that the screening is done in a structured fashion that is consistent with a more detailed method. So once we have a short list, then we're able to apply the detailed method, and we know that we actually picked up the right projects because we are using a consistent method.
Well, I don't know how you did that. In general, that's a hard thing to do, right? Especially with quality. Screens are usually qualitative. And I mean, Tony Cox has a famous paper that suggests that these qualitative methods don't necessarily agree with the quantitative assessments that are going to come later.
Well, I mean, yeah. I mean, one way of doing it, at least, let's say if we take methods such as probabilistic risk analysis, in very simple terms, we can say, all right, it has scenario identification, it has probability calculations, it has consequences, and so on. So if I want to do screening, I need to make sure that I'm considering the right scenarios in the screening, right, at a high level, and I'm assessing the likelihood approximate qualitatively, but still I have some assessment of likelihood and I have some assessment of consequences. So if somebody coming up with a qualitative method that does not account for consequences, then it's not consistent with a more, PRA, more detailed method.
So they should at least have the same units that they're focused on.
Yeah, have the same units. All the elements are covered, or the dimensions are there. There isn't a missing dimension.
Yeah.
So that consistency, I think it's achievable. Would it lead? I mean, unfortunately, some of these items are not verifiable because I can't analyze all the bridges, all the dams to figure out, did I really choose the right list, right? I mean, it could be given maybe a sanity check at the very end, and the people who work with those systems for many years, they know which ones, almost in advance, which ones should be on that short list. I mean, there will be sometimes some surprises, but if they are all surprises, it will be a problem.
Right. The joke about the BP spill and the Gulf was that everybody could have told you what whose rig it was. Nobody was surprised that it was BP.
That's right. I mean, they knew that they knew the deficiencies, right?
Yeah.
But there are problems. But you see, the issue there is that you don't want to have confirmation bias, right?
Yeah.
So I'm just conscious of the time that we've ran over. So I just want to say thank you very much, Professor Ayyub, for having your amazing talk. Yeah, I thought it was wonderful. Made loads of notes, and hopefully can integrate that into my own work. I'm sure I can speak on behalf of the whole institute and thank you for your really interesting research. Where can people find you if they want to kind of follow your work? Do you have like a ResearchGate profile or ORCID, or where can people see that your latest work that you're putting out?
Yeah, I mean, I have ORCID. There is, I mean, Google Scholar, which they collect things on their own. It's quite accurate, I'll say.
Yeah.
And there is my email address. I mean, this is maybe sometimes if you go through those channels, and you might not be able to get the paper easily, and you need to have subscription and so on. But if somebody emails me, I'm happy to share papers. Any documents that I covered today, I'm happy to share.
Okay, fantastic. Yeah, thank you so much. I'll keep the floor open if anyone wants to ask any more questions, but I'm going to stop the recording here.
Yeah, but I'd like to, thank you for hosting for inviting me, and I'm happy to be part of the seminar series. I enjoyed the conversation.
Delighted to have
I know we exceeded the time, but I'm delighted to be talking, conversing, catching up with Scott and
absolutely.
and everybody.
All right. Thank you very much.